Quick recap. Positive metal ions in a sea of delocalized electrons is the definition of metallic bonding. And these metal ions, well, they don't bond to the other metal ions. They're positive. They're going to repel, if anything. Nope. Those positive metal ions are going to be attracted to that negative sea of electrons by electrostatic attraction. Plus attracts minus. Malleable, the definition, they could be bent or reshaped under pressure. With a hammer is another definition. Now, since metallic bonds go in all directions, and not just an individual direction, when I hit the metal with a hammer, I'm going to break a lot of bonds, endothermic, that takes energy. But I'm also going to make a lot of bonds, exothermic, and that's going to release energy. And so since the energy needed to break and the energy needed to make the bonds is about the same, it doesn't take much energy to bend metal. Diamond, on the other hand, those have directional bonds. So if you break those bonds by hitting it, you're going to break the bonds, that's going to cost you energy, but they're not going to reform those bonds. They're not going to bond back to anything else because the direction is wrong. If you're breaking without making, that's going to require a lot of energy to be input. An ionic lattice like sodium chloride, that's quite strong, but if you hit it just right, it's brittle. When you hit it, you can line up the chloride ions and the sodium ions on both sides of the gap. They'll repel and the lattice will simply spring apart. Anything with freely moving charged particles will conduct electricity, and metals conduct, so they must have freely moving charged particles. I've zoomed in on a part of the copper wire here, and you can see the green electrons rushing around in their sea, and the positive metal ions are the brown circles. For no power. If I connect a battery across my wire, electrons will flow away from the negative end, they're repelled, and towards the positive end. And since it's a sea of electrons, or the electrons are delocalized, that means they're not stuck specifically on one ion. They're free to run around where they want. They can flow freely. Metals also conduct heat well. In fact, if you heat any solid, the kinetic energy of the atoms or the ions will vibrate, and that will pass the vibrations along and along and along a wire or something like that, moving the heat along. But metals also have those freely moving electrons. I've only animated one because it was really difficult to animate more than one. You see how fast that moved when I heated it up? The ions are locked in place, but that electron could move really fast. Let's go back and look at that again. So the electron's free to move, the ions are locked in place. As soon as you heat it up, the electron will go very fast and it will transfer its heat energy, its kinetic energy, further down the rod than the simple vibration of the ions alone. And therefore, the heat is going to be transferred quicker. And we're done.